So today I would like to give you an short introduction to control system. We'll use a book from Nice book. And in this introduction, I would like to start with I would like to start with an example so we can understand what is the meaning of a control system. So first, what is the definition, for example, of control system? What is the definition and some examples? So we will start with this. Yes. So control system, what is the definition of a control system? In fact, control system consists of subsystems and the processes which are assembled for the purpose of obtaining a desired output. Given a specific input. So if you can look into this block diagram, you have a block, this block called controlled system or control system. And this system, in fact, it has some inputs. I need to see how can we draw. Yeah. So the system has some inputs. Just input, if your system, for example, is a robot, for example, so it could be the desired speed or my destination. So maybe you have a robot and you want to cover some area, for example. So in this case, the desired input would be a set of points, set of waypoints, and the task for the robot is to follow those the trajectory. So it goes from point A to point B, and when it reaches point B, it should be able to go to the next point, which is C, and so on. It could also be the desired speed, for example. So you want to drive your car at a speed of 100 kilometers per hour, and you are starting from zero. You will use cruise control. So in this case, you will have a set value. So set value will be your desired speed. And after that, the engine should be able to build up speed until it is able to reach 100 kilometers per hour. You have many examples. One of those examples, it's elevator control, for example, which can carry heavy weights to the right destination, considering passengers' safety, comfort, and patience over time. So as you can see here in this figure, maybe you have a passenger who would like to go from first floor to fourth floor. So you have a dashboard in the elevator. You just press 4, for example, and then when you press 4, it should be able to reach your destination. So if it is too slow, people will get tired, right? Because they want to reach the fourth floor as quick as possible. And if it is too fast also, it will be a problem because people will not feel comfortable inside the elevator. So it's a trade-off between safety and maybe safety also is something which cannot compromise, but it's comfort and patience. For example, you can say it like this, comfort and patience. So in this case, we need to minimize time. And at the same time, also, we want people to feel comfort and safe inside your elevator. Those factors we need to consider when we are designing a control system for our elevator. So it will go from point floor 1, right, until it reaches 2, 3, and after that floor, and so on, it will arrive to its final destination. Yes. So how can we measure the performance of your control system? So in fact, there are two major measures of your performance. We can divide the response of your system into one part, we call it transient response, and one part we call it steady-state response. Your system, in this figure in front of you, it's the total response, and in fact, it's the response of your system against time. So over time, we need to plot the response of your system. So in fact, here, if it is the elevator, so maybe you want to go from floor 1 to floor number 4. So my desired input will be 4. I need to reach it. So the blue line, maybe it's the position of your elevator. So you will go from 1, and it will go up 2, 3 until you can reach floor number 4. It will be a problem if you cannot reach floor number 4 exactly, if there is offset between your level and the floor number 4. So in this case, you can see that, okay, we have some steady state error. I cannot reach floor 4, but there are maybe 30 centimeters left or something, and the door will open. So in this case, people inside the elevators, they need to jump in order to reach floor number 4. This difference, we call it steady state error. So we will go back again to the performance of your system. We can divide it into transient response. This transient response, it will happen anyway because it represents the dynamics of your system. If it is too fast, it will sacrifice passenger comfort. So if your elevator is too fast in this period, people will not feel comfortable. And if it is too slow, it will sacrifice passenger patience because, I mean, you have a class and you want to go from floor 1 to floor 4 immediately. You don't want to waste time. So this period, we call it transient response. And after that, we have something called the steady state response or steady state error, for example. And this steady state error, it will sacrifice its passenger safety if the elevator cannot reach the level accurately. So if the elevator cannot level accurately, it will sacrifice safety because you don't want to reach, you want to level with 4 exactly, so people can go from the elevator to their destination safely. So the control system, in fact, it's designed in such a way that the natural response should decay to 0 over time, right? So the total response, we can divide the total response into natural response, which is a transient response, plus forced response. So the total response of your system will consist of 2 parts, the transient response and the forced response. The forced response, as you can see in this figure, it is the one which has been caused by input, by the desired input. So you have some end users, and this end users, he will press a button, he will say that I want to go I want to reach floor number 4. So in the steady state, we need to reach floor number 4. So in fact, this forced response or the forced component of the response, it's due to the input, right? Because I need to reach 4. Maybe someone else wants to reach 6. So in this case, in a steady state, we need to reach floor number 6. So the forced component or the forced response of your system, of your response, it's due to the input, as you can see here in this figure. But the transient response, this is transition from initial condition, because maybe I take the elevator from floor 1. So this is the transition from floor 1 until we reach our destination, until we reach steady state. We don't want this period. I mean, this is a transient or transition, and we want this one to decay as quick as possible because I want to reach my destination quickly and safely. So in control system design, we need this natural response to decay to 0 as time approaches infinity, leaving only the forced component. So this is the most important for us in control system, is to have this forced component. If you are driving your car, for example, you go from, you start driving your engine, for example, or you need to go from 0 until you reach the desired speed. And after that, you need to stay at that desired speed for maybe most of your journey, for example. So in this case, we need to get off. We need to have this transient response, transient component to decay as quick as possible. Unstable system would show a transient response which grows without bounds. This is a problem, and you can link it to the exponential part, right? So if your system is unstable, what will happen? This the transient response or the natural response of your total response, it will not decay. It will grow. It will grow without bound. So it will go to infinity. So as time increases, the transient response, it will not decay, but it will grow without a bound. If a system is stable, a controller can be designed to provide a specific transient response and steady state error characteristics. As I told you before, this transient response, it's a design requirement because in some applications, the transient response part is important and we need it to follow some or to achieve some characteristics. For example, I need to have an overshoot with 10% or with 15% or 20%. This overshoot is very important in some application, such as when we need initial torque. So sometimes we need to design a controller for a system, and the overshoot is important because this overshoot, it will provide us with enough amount of torque which will help us to move. So sometimes the transient response is important, and sometimes also we will not focus only on the steady state response, but also we will focus on the transient response because we want the system to achieve some design requirement. So what are the advantages of control system? So the primary reasons, in fact, for control systems is power amplifications. We have a control system which can produce the needed power amplification. It can produce large amount of power or power gain for controlling heavy equipment, such as elevator, fork, crane, etc., using low power rotation of a knob. Sometimes you have a system like a crane, for example, and you want to control this huge crane which carry maybe thousands of, maybe tens of tons, for example, by just a button or by a knob. So you just will rotate a knob, and when you rotate this knob, you will be able to control a very large elevator or a fork or a crane, for example, using very, very small power. So it's power amplification. So this control system, it will help us to generate this power amplification, which will help an end user to control a very large system, which requires a very large amount of power. Also, remote controlled robot arm, for example, to pick up material in radioactive environment. Maybe you have radioactive environment, for example, nuclear reactor, for example, and it's dangerous for people to be there. So in this case, we will design a robot, and this robot, we will be able to control it remotely. We can control it from a distance. So we'll be sitting somewhere, you have a camera, and you will be able to drive this robot in that location and pick up things like in Chernobyl, for example. So it's difficult or it's impossible for people to reach this location. And instead, you can just send a robot, for example, to pick up stuff and fix things, for example, or maybe underwater, for example, correct? On the seabed, you have also a robot. You can control it remotely for doing some stuff. Convenience of input form also, it will provide convenience by changing the form of input, such as water temperature control during shower. I mean, you want to take a shower, for example, so you want to control your temperature to feel comfortable while taking your shower, for example. So it's convenience of input form. Compensation of disturbances, this is very important. Position control of an antenna, for example, or a crane in strong wind. So it can provide this compensation for disturbance by closing the loop. I mean, we talked about this before. If we can close the loop, the control system will be able to adjust your output according to follow the reference input by reducing the impact of noise, because maybe you are getting some noise. If it is crane, for example, and you are working in a very windy environment, it will be very difficult to control it. So it's very important to use maybe a closed loop system, and this closed loop system, it will be able to compensate for the disturbance. How the control system will look like? There are two major configurations of control system: open loop and a closed loop system. So in the open loop, the system is commanded by the input and it cannot compensate for any disturbance because it's open. So you have your car, you just press a button to reach a speed, for example. But if you are going uphill, for example, the speed will go down. You will not be able to adjust to the desired speed because you don't have a feedback closed loop system. In this case, maybe the person who is driving, he need to look into the meter, the dashboard, and try to increase the speed, for example. But if you can close the loop, so in this case, what will happen? In this case, we will have a closed loop system, and this closed loop system, it will calculate the error signal, and the controller will try to minimize this control signal over time. So this is the advantage of closed loop system. So in this course, in fact, we will not work with open loop system, but we will work with closed loop system because we need to automate things. So we need to have an input or a reference input, and I want my system to follow this input or reference input automatically. So we will not work with open loop. Open loop, it's old scheme in control system because it requires human. In fact, it requires someone to be sitting there watching and fixing the input according to the measured output, for example. But instead of doing this, it's easy just to close your loop and using a summing junction. This summing junction, in fact, it will help you to calculate an error signal. And the task for your controller is to generate a control signal which will minimize this error signal. So there are lots of examples. One of those examples is antenna position control. This is a case study in the book, in fact. This antenna position control. So the purpose here of the system is to have this azimuth angle output of the antenna theta out follow the input angle of the potentiometer. You have an input potentiometer, as you can see in figure A here. You have an input potentiometer. This input potentiometer, it will provide a desired signal, right? And the control signal, the control system task is to try to adjust the position of the antenna. So theta output follows theta input. So we need to get the difference between theta output and the theta input equal 0, right? So in figure A here, this is the concept. And maybe this is the open loop structure if you want to work in open loop. So we need to get a user, and this user, he will just adjust the potentiometer. We need to get an angle of maybe 45 degrees, for example. So the antenna controller, it will just move itself until you achieve this angle, and you will go home. What will happen if you got strong wind, for example? The strong wind will impact the antenna, and maybe it will change this angle. So instead of having 45 degrees all time, maybe it will be, for example, maybe 40 degrees or 38 degrees, for example. What will happen? We will not be able to receive the signal as we want. So in this case, we need to close the loop to avoid this problem. How can we close the loop? We just need to use this differential amplifier in figure B. This differential amplifier and power amplifier, what will happen? The differential amplifier, it will calculate the difference between the input angle, the desired angle, and the output angle. So we will get an error signal. And after that, what will happen? We need to provide this error signal to the motor to adjust. But we cannot provide an error signal to the motor without amplifying it. So in this case, we will send it to a power amplifier, and the power amplifier will be able to generate power, which will drive the motor. So we can adjust theta output. So in this case, theta output will equal to theta input all time. If you got any wind from any or for any reason, theta output has been changed, the error signal will be changed, and the motor will try to fix it automatically. So in this case, we can have a closed loop system. So in fact, the concept diagram in figure E, it's open loop, which requires operator to be there all time to check that theta output equal to theta input. But if you want to save a person, so in this case, we will just close the loop as it is shown in figure B using differential amplifiers. This differential amplifier, it will subtract the input signal from the output signal to calculate an error signal. And after that, the error signal, we will send it to amplifier, and the amplifier will provide the power to the motor to adjust. So it will be adjusted automatically. And in this case, theta output will equal to theta input all time. So there is a block diagram. In fact, if you want to draw it as a block diagram, it will be like this one. So we will have a system. You have a system, motor. It could be a motor or a gear or a gearbox or something. We have a controller. We have the output signal, which is angular output. This is the output signal. We will use a potentiometer. This potentiometer, it will convert this signal into a voltage proportional to the output. So this is a transducer. We call it a sensor or output transducer. So the task for this potentiometer is to measure the output angle and to try to convert it into a signal. It could be a tachometer, for example, right? Tachometer generator. So it could be a tacho. So it will convert this angle into a voltage. And in the input side, we have also an input angle, which we are getting from maybe the operator and the potentiometer. So he will just try, this potentiometer, it's like a knob. He will try to adjust it to generate the desired angle. And we will have a summing junction. This summing junction, it will calculate the error. The error will be the input voltage minus output voltage. So we will get this error signal. And after that, we will send this error signal to the controller, which is maybe power amplifier. And it will amplify it, and it will provide power to the motor. So we can adjust the antenna angle, for example. So if we increase the gain of the signal amplifier, the motor will be driven harder and faster, resulting in overshooting around steady state. Yes, of course. I mean, now we have the controller. If you can increase this power or decrease it, it will control the speed. So we have here two figures in blue. It's output with low gain. This is the output with low gain, which is slow. It will take time because you just make the gain smaller. But if you increase the gain, what will happen? The speed of the motor will increase, and it will make this kind of overshoot and undershoot until you reach steady state. So this gain, in fact, it is a controller parameter, and this power amplifier, we can say that it's B controller. So the design process of feedback control system, in fact, it can be done in 6 steps according to the book which we are using. So in step number 1, we need to find the physical system and the specification from the requirement. We need to find the physical system. And step number 2, we need to draw a block diagram representing your system. And in step number 3, we need to transform the physical system into schematic diagram, for example. So this is a task of chapter 1. And after that, we need to use this schematic diagram to obtain block diagram, signal maybe flow diagram, state space representation, transfer function. We can do this in chapter 2, 3, and 13, in fact. We will start in this course by chapter 2 and chapter 3. And in chapter number 2, we will talk about systems in frequency domain. So you can get the transfer function of your system. And in chapter 3, we will talk about state space representation and the time response of your system. So in fact, chapter 2 and chapter 3 are foundational elements for this course. And after that, we will jump to chapter 13, because in chapter number 13, we can work with controller design. In step number 5, if you have multiple blocks, you can reduce the block diagram to a single block or closed loop system. I mean, it's just a simplification. So if you want to simplify your block diagram, you can do this in chapter 5. And in step number 6, we need to analyze, design, and test to see that the requirements and the specifications are met. So because we are starting in step number 1 with some design requirements, so in step number 6, when you finish your system, you need to ensure that your controller is able to achieve the design requirements. So analysis and the design sequence. So the 6 steps include obtaining the system schematic diagram. To obtain this schematic, the control system engineer must often make many simplifying assumptions in order to keep the model manageable, while it is still able to approximate its physical reality. This system, in fact, it's very important because all systems around you are too complex. But when we try to write a differential equation or a transfer function or a state space representation of your system, usually we make some assumptions and simplifications in order to build a model which is good enough to represent the performance of your actual system, and at the same time, it's easy to control, because if your model is very complex, maybe the equations or maybe the control systems which we usually work with, it will not be enough to. It will be too complex. I mean, it will be too hard, in fact, when you are using a very complex model. So usually people can use maybe second order system to represent all higher order systems. Maybe your system is 5th order or very, very complex system. So in this case, we can just simplify and we can have some assumptions, and we can assume that maybe second order system will be enough to represent my system, and it will be okay. So it will approximate the system behavior, and then when you design a controller, you will be able to achieve your design requirements with some degree. But if you want to make something very, very fancy, so in this case, you need to spend more time to drive equations representing your system, have very complex transfer function or state space representation. You will design very complex maybe controller to achieve those requirements with high precision, for example. So in this case, the cost will be high. So the next step is to develop mathematical models from schematic physics of physical systems. So this can be done in 2 methods, which will be discussed in the next 2 chapters. In chapter 2, we will talk about transfer functions, which is representing the system behavior in the frequency domain. And also in chapter 3, we will talk about state space representations or state equations, which is representing your system in the time domain. So now we are finishing chapter 2, and after that we will focus on we will go to chapter 2. Thank you very much.